Good afternoon, everyone. I hope you are doing all right and ready to learn some physics. So far we talked about charges and how they interact with each other through the force, field, or potential. So three different ways to interact. And we also talked about charge storing device called capacitor. And here is picture of capacitor here, right? So now let's connect a light bulb with some wire in that capacitor or a battery, and you connect a bulb. What happens? It lights. So that means in that case, what happens is charges are moving, charges that are free to move, especially the electrons, right? In the solid like this, only the electrons can move. So because of that, electrons are moving, and that flow of electron is the current. Okay, flow of electrons is the current. So how fast it is flowing, right, and how much charge it is flowing, depending on that, we can tell, okay, whether we have a larger amount of current or a smaller amount of current flowing in the bulb. So that means we can define current as rate of flow of charge. So this is charge that flowed through the wire or bulb, a certain, point on the wire or the bulb over that time interval. So that's what that is. So the unit of current gonna be or can be written as unit of charge, which is coulomb, and unit of time interval or just time, which is second. So that means the second per, coulomb per second is the unit of current, but it is called ampere based on name of a scientist, right? We have seen other units like that. So basically, that's the current rate of flow of charge. If more charge flowing through certain part of the wire at the same time interval, that means we say, okay, more amount of current is flowing. Now, if less charge starts flowing, that means they're going to be less current. So sometimes I may say flow of electrons, sometimes I may say charge. So these electrons, they have charges. So that means flow of electron also means flow of charges. Okay. So that is current. So let's calculate value, tentatively calculate value of current. Let's suppose you are observing there are a lot of electrons crossing a point in a wire during half second. So number of electrons in this case is 100 billion. 100 and billions. How many zeros are there in billion? Looks like million has 6, so billion has 9. So that means amount of charge flowed is number of electrons times the charge of an electron. Okay, so that's what that is. So we can write this as a 10 to the power 11 if we like. So that means it becomes, let's leave it like that. We can plug in later. And then time interval is half second, 0.5 seconds. So that means current is a rate of flow of charge. And in this case, amount of charge that flowed during this time interval is n times E, that many number of electrons, right? And So that means number of electron multiplied by charge of an electron gives us the total amount of charge, right? Like let's say there are 10 person that enter to the elevator. Oh, a lot of people in an elevator, but let's say it's a big elevator. 10% whose masses are on average 60 kilogram. So that means how much total mass got in the elevator. We just multiply number of people times the mass of each person, right? On average. Same idea here. Unlike people, all electrons, they have equal amount of charge. So it's not that difficult. We don't have to think in terms of average. So we can just multiply that. Okay. So now with that, we can plug in numbers. So that N is that, and E is 1.6 to the power negative 19. So the unit of charge is coulomb. So there aren't many numbers here. Maybe you can write the unit. And time interval is half seconds. So let's see that many electrons, 100 billion, okay? A lot of that, right, electrons. But how much current is flowing? Let's see. So half and 1.6 is going to be 3.2 times, and 19 is negative, 11 is positive. So that means looks like we're going to have 10 to the power negative 8 coulomb for seconds. So basically that's what ampere is. See here, typically, let's say if you have a toaster or oven, there may be 20 amperes current flowing through the wire. So that means how many electrons flowing? A lot of them. See, this 100 billion gives you just that much ampere. Okay, so it's small. It's not even a milliampere. Okay, so electrons, the charge of electrons, they are very small. So that means when current is flowing through a wire, what happens? There are several electrons in the number of trillions, and they are moving through the wire. Okay. So that hopefully gives you the idea of what current is, right? So now, when we say, okay, current is flowing, so here what we have is potential difference. So the source of potential difference could be battery. And this is symbol of battery, shorter line and longer parallel line, right? And this negative sign here means negative terminal. Positive sign means positive terminal of battery, okay? So negative terminal have a lot of electrons. So because of that, what happens? Electrons flow from negative terminal. And this is notation for what we call resistance. We'll talk about that soon. So it goes something like that. So if we just talk in terms of how electrons are flowing, what happens? The electrons from this negative terminal, so that's why it is negative, because there are so many electrons, extra electrons. So they basically wants to get away, and whenever they get path, although this path may be a little bit not so easy path, it's gonna flow and go towards the positive terminal where there is more positive charge than the negative charges. So they're gonna start neutralizing, but unlike capacitor, so in case of capacitor, what happens? Once those electrons combines here, the current decreases, but this battery has chemical inside. So basically it keeps on pumping these electrons, okay, over there. So that's why it keeps supply of current constant for a longer time. Okay, so that is flow of electrons. But at the beginning, when they invented charges and current, they thought it's the positive charge that move, okay, in the wire, not the negative charge. So they thought, okay, then it's going to be moving something like this. Positive charge goes towards the negative terminal. That's what they thought. And they said, okay, that is the direction of flow of current. So we keep that convention they used, but now we also know that electrons are flowing this way. So when we say current, direction of flow of current, we always draw starting from positive terminal to the negative terminal. But when we say simply direction of flow of electron, then that has to come from negative terminal. Okay, so that is that. So we call that current, sometimes conventional current, but we simply say current. So it does not make any difference only in terms of, which way the electron circulating versus which way the current is circulating, supposed to current circulating or supposed to positive charge circulating. So it does not make difference other than just this fact. So that's why they did not change the flow of direction of current. Rather, they thought, okay, they said, okay, when we are saying current, let's say it's the positive charge that's flowing, okay? And they kept that direction. Okay, so that's the direction. Oh, now looks like we have a question here. So I'm opening the poll, and it is about direction of flow of electrons and current, both of them. Okay, so path are shown here. There is path number 1, there is path number 2. Path number 3 is going something like that, like a clockwise, and path number 4 is going counterclockwise. So there are 2 paths are given for each choices. So first supposed to be for electrons, and the second supposed to be for current. Okay. So with that said, I'm going to open the poll, and you have a minute to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got for electrons and that. Oh, we have a lot of these. A lot of confusion. More confusion than I thought it would be. Okay. So right here in this slide, we talked about electrons go from negative to positive and current goes the other way around, right? So that's what I said. So here, electrons, so we are first looking at electrons. Electrons go from negative side. So that means it's going to go this way, and this is going to go that way. So current going to be going something like this. Electron going to be going something like that, okay? So that means, looks like electron first means 4, and then current, so looks like D is correct answer. Yeah, a lot of you found this difficult. I don't know what happened. See, this 1 and 2, it's a capacitor, so basically charge don't, these charges, they don't move. Okay, they just stay on the plate unless you are connecting with the wire. Okay? They break down only when there are extremely large number of these charges. Then they can jump through this insulator or air. So this would be direction of electric field actually. If there is no other charge, then that charge can move. Okay. But the charges on the capacitor plate, they don't move like that. Okay. I think that caused that. So I'm glad I brought this question. Anything you like to ask or add here? Okay, I don't hear and I don't see any questions. So let's move on then. Okay. So now what happens is when electrons are moving through the wire or any conductor, what happens is there is some sort of obstacle to them. Okay. So this is basically typical structure of, let's say, metallic objects. Okay. Matters. So matters have what? Let's say the proton and then electrons orbiting around. So there are going to be some free electrons leaving some positive charge. So when they are trying to move, these are attracting them, right? So when they try to move, what happens is it's not so smooth. So they lose energy. Okay. They lose energy just like if these hurdles were not there, then this player would lose less energy than when the hurdle is present, right? So they have to convert their kinetic energy to the potential energy to basically cross that. Okay. So similar idea. So they have some sort of hurdle when they are flowing through the wire. That hurdle has a name. We call that resistance. So device that provides or that has a device that has a resistance is called resistor. So resistor is a device, name of a device that has a resistance, usually high resistance. Okay. And property of the material, this obstructing property, resisting property, obstructing motion property of this is called resistance. Okay. So this resistance is property and resistor is device. So they have two different meaning. We sometimes may just use them interchangeably, but make sure that you understand. So by doing experiment, Ohm found out that the current and voltage are proportional. If you, let's say you have a battery, you have a wire with resistance, and you have a battery that is connected, right? So now let's say if this is 1.5 volt, and let's say you measure current 1 ampere, okay? Now, if you double this, let's say you connect with another battery, by doing that, you are almost doubling this. So now this becomes 3 volt. Now he observes that for the same wire, current becomes double. So that means current and voltage, they are proportional to each other. So this proportionality sign is replaced by a constant, and that constant is resistance actually in this case. Okay. So mathematically speaking, it is just a proportionality constant. physically speaking, in terms of physics, it is that property of the material that resists the motion of the flow of electrons or charges. Okay, so this equation is called Ohm's law. So in short, most of the time we may write just delta V is equal to I times R, or maybe simply V is I times R. Okay, either way, we are meaning the same thing. So unit of resistance can be written in terms of unit of current and voltage by just rearranging this equation, right? So R gonna be delta V over I. So that means delta V has a unit V and current has a unit ampere. So that means V over ampere, and it's called Ohm. Scientist's name is Ohm, and to honor his work, that means we have this. So this is uppercase omega in Greek alphabet, right? So there are lowercase omega, lowercase and uppercase alphabet. So they are basically same thing, omega, but we use this for the symbol of resistance. So I see there is a question on the chat. Everybody can see it. So it loses potential energy because the electric energy gets converted into heat. Yes. So basically, and that's what happens. Although I did not say heat or anything like that, just like our body converts our food into heat, right? So same thing happens here. Yes. So for some material, resistance is smaller. For others, it is larger. So that's why, while, like making electric wiring in our home, okay, these wires we use to connect our devices to the outlet, they have inside copper wire mostly. So copper has smaller, but even smaller is the silver, but silver is more expensive. So that's why we extensively use copper wire for wiring. So usually it has small resistance, okay? So now, although I said resistance is property of material, eh, what happens is resistance depends on what kind of material it is, and if the wire is longer, the resistance becomes larger. But if area is larger, then resistance becomes smaller. And we can tell, like let's say we have this kind of big wire, wide, large diameter wire. So there are going to be a lot of electrons. So there going to be more room for a streamlined room. Okay. Just like, for example, when we are driving in 3-lane road, that means flow of traffic going to be smoother. So in this case, flow of electron is smoother when it's bigger. But if it is just one, lane, like very thin wire, then what happens is that flow becomes congested. So not as much efficient flow. So that's why we say, okay, resistance is smaller. So it depends on area, but larger area does not give you larger resistance, rather it gives you smaller resistance. So they are inversely related, length directly related. So you have to cross longer path of the road. Let's say longer road means you are losing more energy there. And then another important property is it depends on material. Just like I said, okay, same size wire, if you made one out of copper versus one you made out of silver, then copper will have higher resistance than the silver on the same size wire. So how do we differentiate that? So that means we need to take account that different material have a different resistive property. Okay, we call that resistivity, and its notation is, looks like P, but it is not. In physics 1, we use that for density. Okay, here we are using that for resistivity. So that means by combining this information, we can write the equation for resistance, right? So resistance and resistivity, they are related, something like this. So if I like, I can solve this equation for resistivity. Although by looking at this equation, it may look like resistivity depends on area, length, resistance. That is not true, okay? And so resistivity simply depends on what kind of material it is. So if I say, okay, what's the resistivity of copper? So you can look for the resistivity of copper and find out from book or internet. Okay. Copper has a one value, one fixed value of resistivity. And what's the unit? How do we write it? So unit of resistance is ohm, right? And unit of area is meter times meter, meter squared. And unit of length is meter. So one of the meter cancels, giving us just ohm times meter as the unit of resistivity. Sometimes it may also be written in terms of ohm millimeter, same idea. Here we are just measuring area or length and diameter both in terms of millimeter. Sometimes you may see written something like this, but this is the standard SI unit. Okay. So that's what I'm writing here, what I just said. Okay. So now if resistivity is 0, then we say, okay, the conductor is now superconductor, like some human becomes superhuman, right? At least in the movie. But in real life, what happens here? These wires, if they lose resistance, if the resistivity is 0, then we call superconductors because the electrons just keeps flowing. You set up the current in a coil, let's say, and it just keeps running, okay, for very, very long time, for days, okay? So that is called superconductor, okay? So now here question in terms of diameter of wire. So the equation for your convenience, I think it was rho A over L. So that is the relationship we just learned. So what do you think? Thirty more seconds. Five more seconds. Five, four, three, two, one, and it stops. Okay, let's see how did we do. BCD, they are kind of competing. Double camp is a bit smaller. So diameter doubled means area. What happens to the area? How is area of a wire related to diameter? Let's take a look. Pi d square over 4. It's same as saying pi r square. because R means diameter divided by 2. So when you square it, it is pi d square over 4. So pi is constant, 4 is constant. So we are just, we are not changing length, we are simply changing the diameter. So that means we may write this as R as a rho pi d square, and then there is 4, and there is L. So these things we're not changing, we are just changing this. So when d goes to 2d, d squared goes to 2d squared. So it basically picks up this factor of 4. So that means it increases to 4. So B is correct answer. Did I write equation incorrectly all the way around? Let's go back and look. So RA, A is in numerator. So, oh, here, it is all the way around, right? So I did write this all the way around, yes. So now diameter goes to the bottom. So that means decreases to quarter then. Okay, and that's that. Ooh, wrote wrong formula and made mistake. So now over here, it is an example of calculation of the resistance. So resistivity is given, and see, this is 10 to the power negative 8, so it's a small number, okay? So in this case, length is given 4 meter, and diameter is given 2 millimeter. Ooh, small diameter. So let's convert that into meters. So we need to divide by 1,000. So in terms of exponents, we can write something like that. And then resistivity is given 1.8 times 10 to the power negative 8 ohm meter. Now the question is, what is the resistance? So 4 meter long wire. So usually, let's say, 1 meter, 1 meter scale probably, it's slightly shorter than my height. So my height is about 1.5. So that means, so that length of that wire gonna be about the size of. Okay. So usually that's a typical size of, let's say, a wire of, slightly longer than a typical wire we use for, let's say, our toaster or let's say blender and so on, right? So that may be about 1 meter long. So this is 4 meters. So how much resistance they're gonna be, okay? In this case, so 2 millimeter, it's not that, thick wire. So that means we can tell, okay, how much resistance is there. So using this formula, rho L over A, hopefully I did not write that incorrectly again. So pi d square over 4, so fraction of fraction, it goes on the top over there. So 4 times 1.8 times 10 to the power negative 8. And then length is 4 meter, okay. And then pi, the bottom is in calculator, so we don't need to write 3.14, but if we need, we can replace pi by 3.14. here diameter, so 2 times 10 to the power negative 3, it has to be squared. Okay, so looks like there is this 2 squared, so this 1 4 gonna cancel with this 2, so that means this is gonna be 18 times 4 is 72, I think, so that means it's gonna be 7.2 10 to the power negative 8. So you wanna double check with calculator. Often I may make mistake while doing this on my head. And this is 10 to the power negative 6, so it becomes 10 to the power negative 6. When it goes up there, it becomes positive 6. So maybe I can just do this. Okay. So this is around 2. So here I am just writing approximate value times 10 to the power negative 2 ohm. So not that much. Okay. So if you have 1 meter 1 meter wire, you have about half ohm. And if you have, let's say, if you are using that wire for, let's say, a toaster, then usually that wire is thick. Okay, so diameter is larger than 2 millimeter. So that makes the resistance even smaller. So they try to minimize wherever they need larger current. So that's why they put thick wire, right? Vacuum cleaner, oh, the wire still gets warmer once you run that for a little while, right? Have you ever tried feeling the wire of the vacuum cleaner? After you run that for 10, 15 minutes, half an hour, feel that wire, you will feel that warmness. So these electrons losing energy, okay? Heat energy there. Okay, so here is a video about superconductor. Okay, so probably you may have heard or even ridden a high-speed train. I haven't. Okay, so this maglev, I think usually Japan and China, they have built this kind of train. So here is basically theoretical basis. Okay. For some reason, I don't get sound, and I wonder why. Let's see if I can get sound here. Huh. Everything seems to be fine. I don't know why. Sound is not there. Speaker is not muted. I guess Zoom somehow is suppressing the sound. Yep, I could not turn on the sound. But anyway, so that way we can scroll a little faster here. So here you see there is a track, okay? That track is made up of magnet, okay? And here, it's hard to see, but let's see if he showed that thingy. Yeah, you see that it's very cold. You see the smoke coming out. It's not hot, but it is actually cold. Okay. Uh, it is first you put that in the liquid nitrogen so that it becomes superconductor. Okay. Now what happens is this object can just keep going. Okay. So not much resistance there, no friction there because it's not touching that. Okay. And why it can do it? Because it's a superconducting material. Okay. So that was high-speed train. Their track has to be, like magnetic, and they put this superconducting material in the body of the train and put the lot of liquid nitrogen to keep it cool so that it is superconductor. We haven't discovered any material that is superconductor at room temperature. There are certain material we can manufacture and cool them to really low temperature, and they become superconductor. Okay, so that's what you see here. There is a magnet, and there is this superconducting material, also looks like a magnet, but it is not. So that is the smoking cold object. Okay. So right now, see, it's touching, but once you pour that liquid nitrogen, that object becomes, uh, what happens? That object becomes superconducting. That means its resistance goes to zero. Superconductor means maybe very close to zero. So that is, so this nitrogen gas, you can make it into liquid. And but at room temperature, what happens? It starts boiling because its boiling temperature is very low. So anyway, so that's how this magnetic levitation works. So it is a superconducting material. And you can flip it and it's gonna not fall. See, it's not touching. It's close up right now, right? So anyway, so that is the superconductor. So now we said, okay, when current is flowing, the electrons are moving. That's what we said. So electrons are there in the conductor. They are free. They are moving all the time. But without connecting them to a battery or some sort of electric source, current does not flow. Why? Because at those conductors, these electrons are moving randomly. See here, they don't have any particular direction. But once we connect battery or some sort of that kind of electric source, what happens? You see now there is electric field. So now the conductor is in the electric field, means now electron is in the electric field. So what happens? Electron now moves in the opposite direction of electric field. But they are not running really fast. See, this random motion, yes, they are going really fast. Randomly, they are going something like this, but no going nowhere, but moving really fast. The speed is very high for the random motion. But for this, the motion, in the electric field, the direction, the electrons, they are moving in opposite direction to the field. They are not moving that fast, okay? They are moving slow. So that's why the name drift velocity, okay? They are not running. They are just drifting slowly as if a very tiny bug is crawling on a surface, okay? That's how fast they are moving. So this is the equation for the current we said, and this is charge. So charge can be written as number of electron times the charge of an electron, okay? And how much charge is there in whole volume of this? So you multiply that by the volume, okay? So if you do that, what happens is you get this delta x over delta t, where delta x is, let's say, length of the part of the conductor you are interested in, okay? So that basically gives you speed. So that is called drift speed. So here, this is cross-sectional area we already talked about. It's the same thing, pi d square over 4 or pi r square. And n is the number of electrons per unit volume, okay? And this is charge of an electron. So the current can also be written in terms of number of electrons and the speed, okay? So how fast it is moving. So here I have labeled them what they are, right? I already talked about. So now let's suppose you have this information, then you can calculate drift speed. And when we do, what happens is often we get for copper wire, it is like 1 millimeter per second. So it's just moving around a millimeter, okay, in that range. I think our book may have an example. My note, I forgot if I put the example of the calculating drift velocity or not. I think I did, okay. So there is an example of that calculation, and you can see that often this number is very small. So electrons are drifting very slowly. But when we turn on switch, light bulb turns on instantly, right? It does not take very long. So what happens is the wire, they have electrons everywhere. So once you put that electric field, the electrons at every point on the wire starts moving. So that means the everywhere in the circuit they starts moving at once because the electric field gets established on the wire. So that's why what happens? The light bulb turns on instantly when you turn on switch. It doesn't take like several seconds or even minutes, right? If the electron near the switch had to travel and reach to the light bulb, oh, you have to wait 10 minutes or something like that because it's moving really slow. But it doesn't have to be that way. All the electron everywhere starts crawling at the same time. Once the field is applied by connecting with, let's say, battery, then it instantly starts working or moving. Okay. So now, although I already drew it, a simple circuit is drawn something like this. That is, I'm doing it now formally. So there is this battery, and this is the symbol for the battery, and positive terminal is denoted by using longer wire, and negative terminal is denoted by this shorter wire. So battery, we replace that by that, and then wire here, we replace by these lines. And just like we saw, these wires, they have very small resistance, okay? So we say, okay, they don't have resistance here, no resistance. So resistance, all the resistance it has, we just put it there. Usually it is a device or a resistor, okay? So this resistor is the resistance of this light bulb in this example, but could be any. So if you are, let's say, using your oven, then that means the oven has a coil of wire, so that wire has a high resistance, okay? Here, this light bulb, these days we use LED, but back in the days we used to have this wire with this kind of coil, so that means you could see that wire right there. Okay, so that would be the resistance. But now it's a bit sophisticated, not much resistance, very small resistance. So that's why it doesn't get as much hot and it's more efficient, energy efficient, those LED batteries. So they use quantum principle to generate light. Okay. So here there is no resistance in the wire. That's what we assume. Okay. So now let's suppose current is flowing. So what is going on? So we can stretch this like make a straight wire, right? So for example, this side here is, let's say, A, and I'm drawing that A over here, and this side here, positive side. Oh, looks like this is B. and we are going all the way here through the register back to the A. So this is like a, see, with the label A to A means it is closed, okay? So it is closed. So this current is flowing. So the current that is flowing, I'm showing it here. So what happens? Battery has a high voltage. So we are plotting this voltage along the circuit, okay? So this wire, although there is current I flowing, since the resistance is zero, voltage is zero here in this section. So that's why it is just sitting flat, okay, over there. But once it arrives to the battery terminal, there is suddenly spike of the voltage. Let's say if this battery is 5-volt battery or maybe 9-volt battery. I haven't seen 5-volt battery, but I have seen 1.5-volt battery, 9-volt batteries. Let's say this is 9-volt battery. So that means there is this spike. So that is equal to the voltage of the battery. And voltage of the battery is also called electromotive force. We'll be talking about that pretty soon. So EMF and notation is basically that's how we do it. And it is a kind of epsilon, Greek alphabet, okay? This is not uppercase E. Remember, this is for field. So this is not same thing. So battery is a voltage source. So it provides voltage, let's say delta V. But we say, okay, it has EMF this much. Okay. So if it is 1.5-volt battery, that means EMF is that much. And usually what happens is it can provide same amount of potential difference across this terminal. So often this is also equal to delta V, but there is tiny resistance inside the battery as well. Because of that, delta V is often a bit smaller than EMF, okay? So unless we are told we're going to be using this EMF is same as the potential difference provided by this battery, okay? So this EMF going to be equal to potential difference of this battery. They're going to be equal. And then what happens once the electron, let's say, reaches to the point where there is now resistance, it starts losing energy, okay? And once it gets out, what happens? It arrives to this same point as A. So whatever voltage we have over here, this is going to have same voltage. So if we assume negative as a 0 and this has a 9-volt, so how does it going to look like? Over here, 0, over here, 9-volt, all the way up to here, it is 9-volt, okay? And then once it goes to the resistance, what happens? It linearly decreases and becomes 0 again, okay? So potential, we say, okay, potential drops, we say, on the resistor. See, here is coming down. So another way to look at it is this nice picture I found. So what is happening? The EMF, see, in terms of flow of current, let's say this is some sort of charge that's flowing. Let's say in this case, since we are showing the direction of I, we have to say it's a positive charge that's moving, just like our ancestor thought, okay? Now we know it's not the positive charge, it's a negative charge that moves. But since we are showing the flow of current, that means it's, let's say, moving this way, okay? Positive charge moving this way. And then what happens? It is like coming downhill and it loses energy, just like when we go downhill, we lose gravitational potential energy. Kind of similar idea here. So at that point, it emits the energy or radiates the heat, okay? And come back to the same level. So these are at the same level, just like we see here. Here they have same volt. And over there, higher voltage, they have high voltage, but Where the battery is, voltage suddenly increases. Where the resistance is, the voltage suddenly decreases. So that's how the motion of charge in an electric circuit is gaining and losing energy. Gaining means it is receiving energy from battery, and it's losing energy where the resistors are. Okay, so that's how it works, folks, in the circuit. So that's what's happening. Now you can see when there is light coming out from bulb, and that bulb is connected to some sort of source, in this case outlet of our home, and we'll talk about that one soon as well, instead of battery. So in that case, what's happening is these electrons are moving and they are losing energy over there in the light bulb. Okay, and that's what we have to pay to our electric company, our company. So here, to move these electrons from lower level to higher level, this battery has to do work. So how much work it is doing? Equal to Q times delta V, or we can also say Q times, oh, that is my bad. This is not supposed to be, so it looks like my PowerPoint did not recognize the font. It's supposed to be epsilon. Okay, like that. Okay, this is not electric field. This is EMF. Where is that? Oh, here is in my circuit. Okay, that's like that. So either this or that. When battery does not have resistance, we say, okay, it has zero battery. Sorry, zero. When battery does not have resistance, we say, okay, it is ideal battery, like a superhuman. Okay. Okay, so now here is a question for you. So just like we saw over here, see, this can be shown as a this, and we can thought something like this, right? So see how the voltage was changing in different part of the circuit. So this question is about same thing. So it is connected to ground. This symbol is for ground. So that means ground means over there is 0 volt. And on the other side, it is 5 volt. So it is 5 volt battery that is attached to this circuit. So now with that said, I'll let you hold on this. I think a minute should be good enough for this. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. We have B, C, and D. So this skill becomes very handy when we solve problem related to circuits. Okay. So pay attention. It is basically same idea we talked here in the previous slide. See how it is 0 over here on the negative side is like a ground, and the positive side it becomes large, so in this case 5 volt, and then once it crosses the resistance and comes back to the same wire over here, it becomes 0, right? So same idea here, we have 0 here, and then once battery does the work, it has now higher potential, so 5 volt here, and here there is negligible resistance, means it does not lose any voltage, or there is no voltage drop. So everywhere in this part, there is pi volt. So that's why C also has a pi volt. But now, once it crosses this resistance, see, this D and A are connected by simple wire. And the simple wire does not have resistance, so no voltage drop. Same thing goes here, no voltage drop. So that means whatever voltage there is in one side or one corner, it's going to be same on the other corner as well. Okay, so that's that. So all the way here, you have one value of volt, which is pi volt in this case. And on this side, you have just one value. So in the straight wire, you have everywhere same voltage, no matter what you point you look at it, okay? Same. So in this case, it is 0 volt because it's connected to ground. Okay. So now, let's see, BB and BD 0, B and D, no, they are not 0. So that's why this cannot be correct, because BB is 5 volt and BD is 0. BD is 0, BB is 5 volt. And BA is 0. And BC is 5 volt. Okay, so that means, let's see if we have that information here. BB is 5 volt. Okay, that is good. BC is less than 5 volt. No, BB and BC, they have same voltage, 5 volt. Okay, so that's why this cannot be correct. Now, BB is 5 volt. Okay, yes. BC is less than 5 volt. Nope. BB and BC, they are 5 volt. And BD is 0. And so is BA, which is already told here. So it looks like D is the correct answer in this case, okay? Okay, I guess it's a good time to take a break. So let's take a break. Feel free to ask me if you have further questions. Okay, folks, welcome back. So we were in this slide before break. We are still here. Anything you like to add or ask on here? So depending on device, what happens? We lose energy. Some could be heat energy, some could be light energy. For example, light bulb, we get some light. At the same time, it also gets warm or hot, depending on what kind of light bulb you have, right? So that's what's happening in a circuit. And one side of the circuit, as long as we have this just connecting wire, potential does not change on there, but there is drastic change in potential in a battery and drastic change in potential in a resistor, okay? So in resistor, it decreases. In the battery, it increases because it's the source. Battery is a source. So now, so energy is being dissipated. So for example, this coil, it acts like a heater coil, and then it glows, means there is light as well. So that means it's losing energy at a certain rate. So that means change in energy per unit time is called power, okay? So that means when we say light bulb, and probably you may be familiar, 60 watt, 100 watt. These days with the LED, we can get away with 20 watt, okay? So that is the power, means that's how much electrical energy it is converting into other kind of energies. And that's what it means, okay? Rate of conversion or dissipation of energy. And since the potential energy, electric potential energy, is product of charge and potential difference, we can replace potential energy by this. And by doing this, we have now this Q over time interval, rate of flow of charge. And that is what the current is. So power can also be written as a product of current and voltage. Okay, product of current and voltage is power. If we are using EMF for delta V, like this battery, then we can say, okay, it is current times the EMF of this battery. So let's say for this battery, this EMF is 1.5 volt. Okay, so if there are 2 ampere current flowing in this through this light bulb, then we can say, okay, multiply these two numbers. So it's going to be 3 watts. So power consumption is 3 watts. There is another way we can write power, because using Ohm's law, we know delta V can be written as I times R. So power, so delta V is I times R. So that means if we replace this delta V by I times R in that equation, it becomes I times I is I squared times R, right? So this is another way of writing power, power. So here, when energy is being dissipated in a resistor that has a resistance R, then often dissipated energy is written something like this, I squared times R, okay? Because we know the resistance. And there is another way we can write, just like, remember, energy stored in capacitor, we wrote 3 different ways. Similarly, we can write this 3 different ways. So for example, rather than replacing this delta V by I times R, we can replace I. So if delta V complains and says, why I have to leave the equation, cannot that I leave? Then yes, it can. Okay, so we can say, okay, then if we are letting I go, then delta V over R combines with this delta V, giving us delta V square over R. So there are these 3 different ways of writing power equation. So depending on what we know, what we want, we can use one of those. Okay, so now let's look at this question here. It says, okay, let's suppose you have a 100-watt light bulb that operates in 120 volts. Okay, so what is the resistance? Okay, what is the resistance of the wire? That's what it is asking. So power is given, right? So this power is given, so known. Power is given, which is 100 watt. And then potential difference is given, 120 volts. And it's asking for resistance. So if we look these 3 and look at this equation, we can tell, hey, we can use that equation to solve for resistance. So using this equation and rearranging this for R, we can get delta V square over power. So what do we see before we plug in numbers? Let's take a look, okay? See, the outlet of our home is fixed. So that means if we have, let's say, higher power light bulb, that means its resistance has to be smaller. And if we have really a low power light bulb, like a night light we use, dim light, then it has to have high resistance, because power and resistance, they are inversely related in this equation. Delta V is constant because Our outlet over here is basically same 110 or 120 volts, right? But if you go to the somewhere else, let's say different country. So for example, if you go to Europe, they have this 220 volt outlet, okay? Now, same light bulb gonna give you different power over there, okay? So for example, in this case, let's plug in numbers. So 120 times 120 V square, and then power is 100. So this 0 cancels, giving us 144 ohm resistance, right? 12 times 12 is 144. So that's resistance. Now, if it was just 50 watt, then we would be dividing by 50, means the resistance would be double. Okay, so for 50 watt, it would be double, means it is 288 ohm. Now, let's suppose you bring this 100-watt light bulb uh, here in the US and you bring it to your Europe trip, okay? And then what's going to happen? You're going to connect that. What power are you going to get? Okay, see, resistance going to be fixed. It depends just on the coil, resistance coil of the resistance, resistance of the coil. So it's a fixed, right? So now over there, if you plug in that to the Europe, let's say, how do I write Europe? Okay, Europe, delta V could be 200, let's say 40, okay? We had 120, so let's say this is 240 volts. I think it's 220, but I'm using 240 here. So now, will we get 100 watt from 100-watt light bulb? No. So if I calculate this using now this formula, delta B square over R, so delta B square over R, then what's going to happen? The power going to be larger now because it is now 240 square over R is still same 140. See, the delta B doubled, means power became 4 times larger. So if you bring this light bulb and just put that in the, their uh, light bulb holder, what's going to happen? It may just blow the blow this wire. Okay, it cannot handle that much power. It's gonna feel really bright for a moment, and then it's gonna go in a smoke. But now let's say you bring 100-watt light bulb from Europe to US, and it's not gonna blow up, but it's gonna be dimmer than 100 watt. And you can plug in numbers if you like and check that, okay? So why do high power bulbs typically have lower resistance filament compared to low power bulbs? So I'm asking the same question I just talked about. What do you think? You have a minute. Thirty more seconds. Five more seconds. Oh, not yet. Oops. Now 5 more seconds. 5, 4, 3, 2, 1, and it steps. Okay, let's see what we got. So mostly C, that is correct. So low resistance means high current, and high current means high power, if we were to write in terms of that, right? So that's that. So now in our house, we have, let's say, 110 or 120 volts. And battery has just two terminals, right? So when we connect something or to a battery, battery has just two terminals. But our outlet has three terminals. And that third prong we call ground. So some devices, they have just two prongs, right? But other devices, they have three. So for example, our home appliances, like let's say fridge or toaster and so on, they have three. So that does not mean it provides higher voltage. It simply means it provides a path. There is a wire that goes to the ground. So if there is ever a leak, then that's gonna go through that grounding wire. But anyway, so we have this kind of, three wire system in a home. And all these devices, they are connected to parallel to each other. So when they are connected to parallel to each other, each of them are receiving same voltage, okay? Same voltage. Now over here, I'm saying, okay, voltage is 120 volt RMS. So we'll talk about that a little later. Okay, so this is not our battery kind of voltage, it is alternating current voltage. So that's why the symbol you have is not like this. This is a battery symbol, but over here you see circle and there is this wavy sign. Okay, so that means it is AC circuit. So we'll be talking about AC pretty soon. So what happens? They are in parallel. So they each of them independently gets their voltage, and we can turn off selectively that way. If we were to connect them in series, what's going to happen? They, if we try to turn this thing off, then this is going to be off as well. Okay, because they are in series. But in parallel, we can put the switch over there and just turn on and off just this or that or that. Okay. So in parallel, they receive same voltage. Okay, so that's why all the light bulbs we design, and they assume, or all the device, they assume usually, it's 120 volts. They operate under 120 volts here in US. Okay, so now alternating current, I said, okay, so how is alternating current generated? So for that, we need a fixed magnet. Okay, see, north and south pole. Yes, we cannot just break a magnet and make south pole, north and south pole out of that. It's just simplified version. There's going to be south pole. There has to be south pole here. There has to be north pole. We'll talk about magnetic property later in another chapter. But let's say we have this magnet that provides magnetic field, okay? And there is this coil. So this coil, you have to rotate. So for example, let's say if you are generating electricity using wind power, then see there is this big fans, right? So because of that, it rotates that fan. And now this coil is connected to that fan there. And because of that, when the fan over there, due to, air, when the fan is rotating due to the air, then this coil rotates here, okay? And when it starts rotating, what happens? It generates current. But this current is not direct current. So that means you cannot just you can say, okay, the current goes this way and then comes out this way and so on. Rather, what happens is, since the coil is changing the direction, the current is also changing direction. So because of that, we say, okay, we get alternating current. See, they have this coil. There is this handle. You can hold on that handle and rotate that coil in the magnetic field, and that's going to produce current. And see how current is going left and right. So on average, it's going to be 0. See, it goes as much left as to the right. So that means on average, it is 0. So that's why we need that RMS thingy. Okay. So we have to we have to design a special kind of meter to measure this kind of current. So when coil is rotating, what happens is it produces this EMF that is kind of changing with respect to as a sine function or cosine function, right? Sinusoidal function. So it oscillates, goes to maximum value, and then goes to the maximum value to the other side. So I wouldn't say minimum value. Minimum value would be 0 here, this line, right? And this value over here is square root 2 of that value. So slightly less. So where that number coming from? Let's talk about that. So now let's suppose you have current, you have voltage. So that means if you want power from current and voltage, what do? You multiply current and voltage, right? So equation for the alternating, let's say voltage is this, is changing as a sine function. So we have to write like that. And the maximum value is the amplitude. I guess that is that over there. And this one is over there. So we are just multiplying current and voltage. So this is maximum value of current and voltages in the cycle. But this here is the sine and there is the sine. This omega is angular frequency, rotational rate of this coil. Okay. Remember frequency and omega is 2 pi f. And frequency is 1 over period. So the sine omega t becomes sine square omega t, and we are left with this. Okay. So now the sine square function, now see the power depends on sine square function, and you see this t on the parenthesis there. So that means it changes with time. That's all it means. That does not mean we are multiplying with time. We are not. Okay. So it changes with time. And how does it change? It goes like a sine function almost, but it does not goes to the negative side, because when you square a negative number, it becomes positive, right? So it's always positive. So how much power this thing is delivering? Sometimes 0, sometimes this maximum value. How much is the maximum value? That's what the maximum power is, product of maximum current and maximum voltage. Okay. So now on average, it's going from 0 to that maximum, means average power is half of that maximum. And that's what we are writing here, average. So there is this 2. So we can divide this 2. See, the 2 is same as square root 2 times square root 2. So we can, let's say break this into 2 factor and stick one of those underneath the current, maximum current, another one underneath the voltage. And that's what that is. And those numbers are called RMS value, root mean square value. Okay. So those are called root mean square values. So now in terms of root mean square, it's just product of current and voltage, like our DC thingy. So this is like a DC equivalent. DC means direct current equivalent equation. Okay. But RMS value, basically, when we are measuring, that's what we are measuring. So when we say, okay, we have, let's say 120 volt coming out from our outlet, it's not just 120 volt. The 120 volt is RMS value. But that value can go from, 0 to maximum value. And how much is that maximum value? So see here, the RMS value, for example, VRMS is maximum V divided by square root 2. So that means maximum value, also called peak value, because these are the peaks, right, is square root 2 times RMS value. So that means from our outlet, voltage sometimes is 0 second, sorry, 0 voltage is 0 volts, and then the maximum value can go all the way up to square root 2 times whatever said value. So that means, let's say square root 2 times 120. I think that turns out to be around 170. So it goes from 0 to all the way near 170. So that's how it's changing. But it's changing very quick. How fast? We say, okay, frequency is 60 hertz. So that means every second, it's changing 60 times every second. So it's changing very quickly. Okay. So anyway, so that's the kind of thing we use. That's what comes in our home. So when we plug that in our computer, inside a computer, there is this thing called adapter. So it converts this AC into DC. So our devices, these electronic devices, they use DC, but our home appliances, they directly use the AC. For example, oven uses AC, washer, dryer, all these uses AC, but your laptop AC, your your laptop DC, your phone DC. Remember your phone, the charger of your phone that has a little bit this thingy there, bulk there. So it is that device that converts the AC to DC before getting into the phone. And some computer laptops, they have that kind of thingy as well, right? Do I have that thing somewhere here? Maybe, but not in my hand, so I'm not going to look for that. You know what I'm talking about. But you may have desktop that directly takes AC. So that means that converting part, that power supply is inside the computer. Okay. So anyway, so that's the AC. Oh, that's the RMS values. Okay. So average power can be just found by multiplying this. Okay. But if you are multiplying the peak values or the maximum values, then to find the average, you need to divide that by 2. Okay, so that's how it works, folks. So now here is a question for you. So what do you think based on what we just talked about? Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. So mostly B, that is correct. That is the RMS value of voltage, okay? So whatever power rating or voltage written in your device, that is RMS voltage. And that's what the ammeter or voltmeter measures. So we said, okay, some of these home appliances, they have 3 prongs, right? So one prong, we say, okay, that is live, or let's say, it doesn't have like a positive, negative in the sense of a direct current. So that's why we don't say positive or negative. Rather, we say, okay, it's active or live. Okay. Another one is neutral, and third one is ground. Okay, that's what we call. And the ground, when you plug in, what happens is that device, that third wire goes and somehow connects to the body of the device. Usually many devices, they have metal body, right? So what happens is, let's say somehow, let's say some current leaks from some electrons. Now we know current means electrons. Some electrons leaks from the wire and wants to go to roam around here. Let's say there was wire, and this wire has a plastic cover, of course, and sometimes it may break. And now it becomes naked wire, and that from the naked wire, if that naked wire is touching the body of the device, then in that case, what happens? Some of the electrons gets into that body of the device. So for example, in this case, refrigerator is shown, and you go and toss the refrigerator. What's going to happen if the ground is not there, full of electrons there, and now it finds your body, which is conductor. It's going to go, it's going to go through your body, especially if you have, let's say, no rubber sole shoes or something like that, and you'll feel that. Okay, so to avoid that, what happens, even in the case of leak, what happens, these can just go to the ground safely, because the wire has a very small resistance compared to our body. So whenever they find wire, metal wire, they want to go through the metal wire rather than our body. Okay, they want to go to the least resistance path. It's like saying, okay, there is one road, a lot of traffic, and there is another road, not much traffic. What would you do? You will drive in the road that has less traffic. Kind of similar kind of thing, okay? So flow of current is like a flow of electrons, right? Like a flow of traffic or flow of water in a tube. Same thing. So water molecule over here, in case of current, it is electrons for the wires, okay? And when we're talking about outlet, probably you may have seen something like this, okay? So that has a, what is this so special is it has now an extra coil inside and these reset buttons, okay? This is called GFI, ground fault interrupter. So if you look, what happens is behind the scene, you have this coil, one extra coil other than the wire. So what happens? This coil senses the current, how much current is going and how much current is coming back, right? So if it finds there is less current is coming back than going, and then what happens? It says, oh, there is leakage of current. So it's going to break the circuit, okay? So that's how it interrupts. And usually it is designed to interrupt when current, incoming current is 5 milliampere less than the outgoing current. So why 5 milliampere? Because if more than 5 milliampere current goes through our body, then it may cause, damage to our heart, our body part. Okay, so for that safety, that's what it is done. Ooh, looks like I'm bringing the same question here, so I'm not gonna pull on that. So now we have this question. Let's say you have a hair dryer and the power. So hair dryer, if you see there gonna be some sort of sticker and there gonna be number, there gonna be voltage written, and it may say power. Okay, so next time when you pick your hair dryer in your hand, take a look what numbers are there. Okay. So over here it says, okay, power is 1160 watts when plugged in. So that many watts when the potential difference is 120 volts. Okay. Now part A, it says, okay, what is the amplitude of the voltage coming out of the outlet? So it's saying voltage maximum is what? Amplitude means peak value. Okay. Remember we represented voltage or EMF something like this. So it has high value, it has zero value, right? So that is the B max. So that's what it is asking. And this delta V means since delta V 120 volt is BRMS, V max is more than this. How much? Square root 2 times 120 volts. Just like I said before, it turns out to be around 168, something like that. Okay, I don't quite remember, but punch in your calculator. So now B, it says, what is the resistance of the hair dryer heating coil? Okay, so larger, way larger power than light bulb, right? And in light bulb, it was like 100, 140 ohms when it was 100 watt. So it better be way smaller resistance. So it's asking us, where is that question? Now, looks like I need to get rid of this. Hopefully you have this now. So now R is what? And remember, the formula we wrote worked for the RMS values, so we don't use peak value for that. So R is V square, VRMS square over power. So that means, hopefully I wrote this formula correctly. So R is V square means 120 square and power is 1160 watt. So that's gonna give you the resistance. Okay. So it's gonna be a lot less than what we had for a light bulb, which was around 144 ohm. Okay. So it's gonna be around 10 times less. Okay. So numbers, I will let you punch that. Now the part C, it says, what is the RMS and peak current through the dryer? So now we have resistance. So it's asking us RMS and peak current, okay? So our formula, usual formula that works with the DC as well, that is for RMS. So we can use RMS. We can calculate RMS like a VRMS over R. So once we do that, it's going to be 120 divided by whatever number you got there. Okay. How about peak? So now to find peak value, peak or maximum value, there are two different ways. One, since you also figured out B maximum, right? You can use B max over R or I max or peak is square root 2 times I RMS. Since once you calculate that, you can put that there. Okay. So here, what you need to be careful while writing this formula works like a, DC formula, but if you are using peak current, then you need to use peak voltage. for the power, let's say, and that's going to give you the maximum power. For example, if you are finding current maximum, then you need to use Vmax, okay? But I'll remember this, power is IRMS. So all these are in terms of RMS. Whenever I need maximum or peak, I just multiply that particular quantity by square root of 2, okay? But power, you have to multiply by 2 to get peak value. So for example, what's the maximum power? It's going to be 2 times this RMS power here, okay? Okay, so when we are using electricity, we have meter, may not be exactly like this, but we have this kind of meter, and every month you get, oh, you use this much, and it says unit. So what is that 1 unit? 1 unit is kilowatt hour. Oh, what is that? Watts, we know. Kilo means 1,000, we know that. Multiply by the time you use. So for example, you have a 100-watt light bulbs, and then you run that for 10 hours. And how much energy did you consume, right? So longer you light the bulb, you are using more energy. So basically, that is the unit of energy, not the unit of power, okay? So power times the time gives us that energy, because power is rate of transfer of energy. So we can rearrange that. So the unit going to be joule or watt times seconds, but in our home, it uses kilowatt, and instead of second, it uses hour, and that's called 1 unit energy consumed, okay? So that's what I have written here. So now let's suppose you have a laptop that is taking 240 watts, and there is a space heater. Probably you don't use that, but I'm saying that. And then a light bulb, and you run all these for 5 hours. Okay, so that means how many units did you use? Find the unit, and then now multiply that by the cost per unit. Oh, this has gone higher now. Okay, so that way you can get the total price. So now here, what's happening? You have this 240 watt. So if you want kilowatt, you can convert this in kilowatt right away. So for example, one gonna be 0.240 kilowatt, right? And then another one gonna be 1.380 kilowatt. So I'm writing in terms of kilowatt because unit is in kilowatt. And then another one is 0.0, just 120 kilowatt. Okay, so that is power, total power in kilowatt. So you add these numbers. So how much is that? Ooh, 3, 4, and 2 is 6. Ooh, around 1 point, let's say 7. You do the math, okay? Around that much kilowatt. And then now, how much energy you spend? So that is power times time interval. So time is in hours, so we don't need to convert anything. So it's going to be that power, whatever number you get here in kilowatt, times the 5. Okay. So that is kilowatt hour. So that is that many unit. Now multiply that unit by the price per unit, and you have your electric bill. So that's how they calculate energy used in home. Okay, so this is a general introduction of current, and the next class or next 2 class, we're going to be talking about how to solve problems, okay? And I think after that, there is a midterm coming. First midterm is coming after the currents, okay? So it seems like we just started. Now there is first midterm. Okay, folks. So I'll let you go. If you have quick question, stop by and ask, or else I'll see you next class or next Zoom hour.
Thank you.